Now let's analyze this solution a little bit because it's fascinating. Remember, PDEs give us a relation between how things change in space and how things change in time. And this heat equation is the first equation that we've solved that actually has both space and time. Remember, in chapter 5, it was only space. So now, here's how space and time are related in these solutions. Notice everywhere in the solutions, there's the time is in the decaying exponential, and the x is in these sine functions. And so here are some notes to look at here. The frequencies in x depend on this n, and when we look at behaviors of functions, we usually associate smooth behaviors with low frequencies, like things are moving slowly, so it's like with a low frequency. And if things are moving rough, we associate that with high frequency, rough meaning like changing a lot. And so high frequencies would mean higher n. Higher n, look how if n gets higher, n squared is really getting higher. For high frequencies, for high n, the decay rate in time is faster. And so the idea is that if we start with rough conditions in the initial condition, like when these things are multiplied with the GNs, if we start with high GNs, like high frequency rough behavior, that gets damped in time faster. The damping constant is higher than for low frequency behaviors. So that's very interesting. In fact, notice that as soon as t is positive, these solutions are smooth. So even if the initial condition was not smooth, this becomes immediately smooth. And by smooth, we mean we can take derivatives of this. All the derivatives exist. We can take derivatives an infinite number of times. So it's very smooth in that way. Notice that while this is exponential decay in time, there's the sense of heat when heat diffuses, or when heat is conducted, it goes down, it exponentially decays in time. This e to the minus n squared, if we were to graph n, meaning the frequencies of those behaviors, this time function here would have the form e to the minus n squared. That's a bell curve, the shape e to the minus n squared times all those other things. So for each snapshot in time, if we looked at this as a function of n, there's a bell curve there. Did you know that there are a lot of interesting physical models where heat is considered to be a statistical phenomenon? If you think of particles, heat being caused by particles in a fluid running into each other or bouncing off of each other, and that generates heat. It's like you put a lot of particles together. That's a statistical thing to look at the average of that ensemble of particles. And indeed, bell curves show up in both heat, PDEs, and statistics. Never bet you thought you would see PDEs and statistics being the same thing when you first signed up for this class. But there's a real reason for that connection. And finally, the last thing to notice is that this kappa over rho c shows up as a unit. It shows up as a group. And also x over L shows up as a group. If we make the substitution y equals x over L, then these things become sine of n pi y. And the eigenvalues become n squared pi squared. We don't even need the L squared up here. That's a nice way to simplify this. If we take our coordinate system, and remember, we were looking at a domain that went from 0 to L, if we scale the coordinate system so that instead of having 1 be some unit like this, if we scale things so that our unit 1 of measure is right here, everything goes from 0 to 1, then that simplifies this quite a bit. So when x goes from 0 to L, y goes from 0 to 1. If we also make that substitution of s equals the kappa over rho c and times t minus t0, look how nicer the solution is. We would always have these forms as e to the minus n squared pi squared s, and then we would have sine of n pi y. No more L's and no more kappas, rhos, and c's. All those parameters simplify, and we see just the dependence on y, which is like our stretched space, the dependence on s, which is like our stretched time, and then the eigenvalues, n pi, showing up in both places. So remember, these things not only get multiplied by Fourier coefficients of the initial condition, the GNs, if we have a non-homogeneous PDE with the equals f instead of equals 0. These things become the convolution integral, or they are convolved with the Fourier coefficients for the Fn. So these are really the fundamental structure of the solutions to this equation.